So good morning. So this was work inspired by a blog post that some of you may have already read from Greg. It was back in 2021. I know at least a couple of people who kept that Jupyter notebook among the favorite ones, because it's pretty nice, because it allows you to highlight the different R groups that you extract in the original molecule. So you can immediately see at a glance where R1, R2, R3, R4 are in the original molecule. But the way that blog post worked is that the implementation was written in Python. So you needed the code in that Jupyter notebook. And more importantly, that needs a number of low-level access functions to molecule and atoms, which are not available from JavaScript. So Datadog wanted to implement this sort of visualization in their JavaScript-based tool. And so I thought that it would have been useful to implement this straight in the C++ layer so that it can be accessed from Python, Java in 9, JavaScript, and so on. So this is actually quite simple. Here I'm just switching on the interactive renderer in the Jupyter notebook. This is something that I presented a couple of years ago, and it enables some JavaScript magic inside the Jupyter notebook or inside your JavaScript web application if you're using it in your department or company. So what I'm doing here is just loading CSV datasets downloaded from Campbell into a pandas data frame. And this is the core that we are going to use for the decomposition. You can see that I switched on the interactive rendering, because when I hover on the molecule, I now get a widget for copy pasting and one for doing something interesting like redoing the layout using either RDKit or CoreGen. And I can also do copy paste of the molecule in different formats, smiles, small block, inchy. Here we don't have the inchy because we have dummy atoms. I do R group decomposition with the standard parameters. The only parameters that I added was one to include also the target molecule in the results, in addition to the core and the R groups, because this will be useful when we will do the visualization of the highlights. And what I get back is a list of dictionaries. In each dictionary, you have the core and the R groups keyed with the respective label name. And since I included also the target molecule, I also have a key for the molecule itself. And then here I just have a simple helper class where I set the color maps. These are the same color maps that were used in the original Greg blog post. And this is just another helper function which takes the indices into the main molecules, which are now attached to each R groups, and sets the highlight with the respective color in the original molecule. Here we have 7 R groups extracted. I only highlighted the first 4 as Greg did in the blog post, just to avoid cluttering the picture too much. And then I did the same kind of visualization that Greg was doing in his blog post. He was stitching basically all the molecules in a big PNG using Pillow. I did the same just to show that you can get exactly to the same result. And this is what you get. So each R group is highlighting its own color, and you get all the molecules in a big grid. But thanks to the interactive rendering, which is made available by the JavaScript layer, you can also do something slightly more interesting, because you can actually visualize the whole pandas data frame with the usual pandas tools trick. But additionally, in this case, the molecules in your table are also interactive. So you can also do copy pasting, as I showed, or you can relay out if they were body laid out because they have some body initial coordinates and things like that. In this case, usually you don't want to do that because I have already laid them out such that they are all aligned with the core. So that's not a functionality that you would use. And just to reiterate, in addition to the visualization part, you can also do directly the R group decomposition from JavaScript. So if you have a web application and if you want to do the R group decomposition, you can do it directly in the browser from the JavaScript layer. That's all.
Are there any questions about it?
Thank you.
I think that original blog post was actually inspired by some stuff that you and Dominique had done, right? Look familiar to you. Okay, so I'm just going to go back to the notebook. Again, this notebook is going to be in GitHub. It's not there yet because I'm not done with it, right? It's still a bit of a live work in progress, but it'll be there in the next couple of days. I want to start with a somewhat of a larger topic, and this is something we added in the current release, so the 2024-03 release cycle, which is support for dealing with isomers in the RDKit. This is something that Tad at CDD did. We all worked together on this, and he came up with an idea for a representation and how we might do this. And it's been there. And I want to just walk through what's there so you understand it, because I think it's pretty important. This is something that's becoming more and more relevant. And it's something that we didn't have a analogy in other toolkits to look at and see how they're handled, because most toolkits don't do this well or at all. So I just wanted to let you know what's there, and we can talk about it a little bit. So the basic idea, for those who don't know, an atropisomer is a rotationally hindered single bond that gives rise to chirality. So this molecule does not have any chiral centers in it, but the molecule itself is actually chiral because you cannot freely rotate about this single bond, right? So you basically have four different atom types around the bond that make it chiral. That's an atropisomer. What we're doing in the RDKit is pretty simple. So we have the following set of rules: that if you have a single bond or a potentially rotatable bond in the molecule, so a non-ring bond that has sp2 centers on either side of it or on both sides of it, and there is those neighboring bonds are single, double, or aromatic, and you have symmetry and equivalent groups on each end, and there is a wedged bond, then the RDKit will interpret this bond in the middle as being an atropisomer. For those of you who've dealt with this before, the immediate thing you're going to start arguing about is whether or not the bond is actually rotationally hindered and whether or not it really is an atropisomer. The RDKit is not attempting to solve that problem. That is a problem that you have to do a high-level quantum calculation. You need to know the temperature and you need to know the solvent that you're in. We are not doing that. It's like the tautomer thing, right? We don't try to give you the right tautomer. We give you the canonical tautomer. And in this case, we believe you when you say that it's an atropisomer. So if you don't want it to be an atropisomer, remove the wedged bond. So hopefully nobody in this room will now have that argument, but I'm looking forward to these arguments on GitHub over and over again. So that's the basic idea. So if you do that, the RDKit will then recognize it as being atropisomeric. And if you take the molecule and you do debug, you can see that it's recognized the thing as being an atropisomeric because the bond now has a stereo code, which is counterclockwise. And it gives you the ordering of the bonds, of the neighboring bonds, these single bonds. This, by the way, all of this documentation and these examples are taken from the RDKit book. So you don't need the notebook. This is already in the online documentation. This is the atropisomer stuff is integrated into the SIP assignment. So if you assign SIP labels and then display them, you get the proper M or P labels for the atropisomeric bonds. The information is used in conformer generation. So if you have an atropisomeric bond in your molecule and you generate conformers, you will only get conformers that have the correct atropisomeric configuration. So the correct configuration about that single bond. If you see something else, it's a bug, please report it. But you should expect that you're going to get the correct configuration about those bonds. The representation I'm not going to get into. This is in the book. I could spend the rest of the time talking about this, and probably you might still be confused. The other thing is it can also perceive atropisomeric geometry from 3D. So if you have a 3D structure that has one of these bonds that might meet the requirements, and you include a wedged bond in the conformer, the 3D conformer, it will perceive the actual geometry from, or the atropisomerism from the 3D coordinates. The wedged bond is just there to mark that you want that bond to be interpreted as atropisomeric. Anybody have any questions about that? Because I'm not sure I explained that well. Yeah.
Is Is the marking of atrofisomeric centers gonna be automatic, or do we have to like manually enter?
So the question for people online is whether or not that's automatic, and it is automatic. So if you have the bond, the wedging in the bond or in the structure, it will be recognized when you parse the molecule. Yeah, Peter.
Maybe check that at least 3 or 4 orthopositives are substituted, otherwise cannot be orthopositives or anything.
So again, we're not having that argument. If you, you're correct. But once you start down that road, then you end up with lots of things about, well, why don't you include this case? And why don't you include this case? And then somebody says, yeah, but we're working at absolute, or at liquid helium temperatures, and then somebody else is in a different solvent. And if you wedge, only if you wedge the bond, right? So if you give a 3D structure where you do not have a wedged bond, it will not interpret it as atropisomeric. So if you explicitly mark one of those bonds as wedged, then it will do the interpretation. Feel free, for those of you who like this topic or who feel strongly about it, feel free to write code that recognizes things that should be atropisomeric and adds wedge bonds. I know Richard is looking forward to doing this. Yeah, he's done it already. We don't talk about OpenAI here. So for people online, what Richard said is they're working on code which I think is going to be open source or is already. Okay, it will be open source, and they have some way to tell Omega to do this too. Yeah. Yeah. So the question online is what about the cases where you just have an arbitrary input file where maybe people drew things improperly? So if it meets all of the requirements and the 4 substituents are different, it is going to be recognized in the atropisomer. And like we always do when we deal with inputs coming from arbitrary sources, you really need to clean those up before you can work with them anyway. So this would be a case of you would need to clean it up when it comes in. So it would be really part of the standardization pipeline. But I don't think it's going to happen that often. Normally, when people draw these bonds as wedged, it's because they're trying to indicate the stereochemistry. Any other questions on that? Okay, so as I said, that's already in the release. It does require coordinates because it needs to know where things are. There's a way to do it using CX smiles where you don't have coordinates. There's a convention that we're using. I'm not going to get into that again because it's complicated. It's described in the notebook, but it's also in the documentation. So you can do this without having a 2D conformer. Yeah, about that. Because you don't, but you need to have a convention where you agree upon what the wedged means. And that's what's in there. So you need in the documentation, it explains what the convention is. It's not 100% clear. You need to just decide if it's wedged up, it's clockwise, and if it's wedged down, it's counterclockwise. And that's the documentation. It explains that. Any other questions about this? Yep. I hesitate to repeat this for the online. So the question is, what about other types of axial chirality like allenes? We have everything there now that's required to support those, but it's not there yet. So that's a very good question. The other, for people who don't know this, so if you have 2 double bonds in a row, 2 sequential double bonds in a row, you also have a tetrahedral geometry, and so consequently those things can be chiral. If you have 3 in a row, it's a cumulene. And then it can be cis and trans, right? And so 3 is cis and trans, and then 4 is chiral again, and 5 is cis and trans, and 6 is chiral again. We don't yet support that, but we have everything. The changes that were made for the atropisomers allow us to get there, and hopefully it will be there at some point in the future. Other questions on this? Okay, I'm pretty excited about this. I think it's useful. It's really useful functionality. It is also the information is taken into account when doing canonicalization. So if you're doing canonical smiles and do the CX smiles output, you get a canonical representation of this. So you can actually use it in registration systems. Okay, that was that one. The cartridge was mentioned a couple times yesterday. I'm not going to say a lot about the cartridge right now. One thing I do want to mention, because I think it's really just deeply, profoundly useful, is you can now Conda install the cartridge. For people who don't know that, so it's just like installing the RDKit normally. So Conda install from Conda Forge, RDKit Postgres, and you get the cartridge. It'll also download Postgres for you. I'm going to do a blog post that explains how to get the thing running. This also works on Windows, which is super cool. And it is part of the normal Conda Forge board build process for the RDKit now, so it will be kept updated as the RDKit is kept updated. So I think this is really nice, because if you've had to deal with the cartridge before, you may know that you have to build it yourself. And if you're not like me or Paolo, that's a giant pain in the ass. But now it's easy. And I'll say some more about the cartridge later. Yeah.
Default version coupling, because when you're installing RDKit and Postgres, then we have two entities with different versioning. So is there like,
So you notice this is using Conda? Conda takes care of that for you.
yeah, but what I mean is there like official advice coupling of versions? So for this version of RDKit,
If you install it with Conda, it will install the right version for you. And if there, at the moment, there's not a requirement, if there is a requirement, we will make it part of the Conda package. This is one of the big reasons we use Conda, is it makes it easy to do this stuff. And so this makes it all easy. If there ever is a tight coupling, it'll be reflected in the Conda package.
I think the question was more if you have your own RDKit version or you can customize or you link to the Postgres.
So if you have your own RDKit, then you have to build the cartridge yourself. You can't Conda install it. Right? This is for if you're using Conda to install the RDKit, you can now use Conda to install the Postgres cartridge. Other questions? Alberto? No. So well, you could, but you would have to copy the files manually. So you'd have to make sure that the local version of Postgres that you have is the same as what gets installed by the Conda, and then you would have to manually copy the files from one place to the other. Yeah, if you have an historic database, you really need to do the build yourself. This is really set up for if you're using the Conda Postgres install. Okay, other questions? Good. So we have not a huge amount of time for this session. I'll do another couple of quick ones. This is on some performance things. Oh, come on. I was saying nice things about Jupyter Notebook yesterday. Okay. So one of the things we've done is exposed more capabilities from within Python to have C++ run stuff in parallel in the background. For those of you that are not developers, I call this multi-threading. So it's doing multiple things at once on the C++ layer. So you don't have to worry about it on the Python side. Because as was mentioned yesterday, doing this in Python is not a trivial thing. So this is an ongoing effort where possible and where it's sensible, we're making it possible to do things in parallel. So if you're working on a bunch of molecules at once, instead of doing one at a time, you can do them in parallel, just on your laptop, basically, or on your workstation. So the first one I'll talk about is using mol standardize. So for people who don't know that, this is for doing things like standardization, molecular standardization pipelines, or doing salt splitting, neutralization, and stuff like that. What I'm showing in this example is I've loaded a set of around 4,500 molecules. I'm importing mol standardize. I'm turning off mol standardize is very verbose. It sends a lot of stuff to the log, and this is just showing you how to turn all of that noise off. So if you don't want to see all of the log messages from all standardized, you can just turn the log off and you don't need to worry about it. And then I'm showing the performance difference. So here, the first thing is that the normal standardized code takes a molecule, changes it, and gives you a new molecule, which is the changed molecule. So the default version of normalized takes the input molecule and gives you a new molecule. And to do that across the 4,500 molecules takes 1.6 seconds. Most of the time when you're changing a molecule, you don't care about keeping the original one. You're perfectly happy having the original molecule get changed. So we added something called normalize in place, which takes the molecule you give it and edits that molecule. And that turns out to be a lot faster because we're doing less copying and duplication. So here in this case, it only takes 1.2 seconds to do it instead of 1.6. So you save some time there already. And then the other new piece of functionality is normalize in place will take a list of molecules instead of a single molecule. And if you do that, you can tell it the number of threads to use. This is the number of molecules to work on simultaneously. And you can see now it's only taking 200 milliseconds instead of taking 1.2. So I told it could run 4 threads at a time, and it ends up running a lot faster. So this is just these kind of simple, embarrassingly parallel things where I need to work on a bunch of molecules and do the same thing to them. It's now easy to do that from Python by just letting the C++ do it for you. Any questions about that? Yeah. So if you give the num threads equals 0, it'll use all the threads that are available on your machine. I would be wary of that because if you have hyperthreads, which almost everybody does, it'll use all the hyperthreads, and you don't get the performance gains from hyperthreads that you do with normal threads. But you can give 0 and it'll do. So like if you have apologies for the details for people who don't care about this. If you have a Xeon processor and you give it 0, it actually does a pretty good job. But if with the normal i9s and i7s, it doesn't, it's normally better to just specify the number of threads. But you can always give it 0. You just don't get maximum performance. Other questions about that? Okay. You can do the same thing for fingerprint generation. So the fingerprint generators, there's this get fingerprinter function where you give it one molecule and it gives you one fingerprint. You can also call get fingerprints. And if you do that, you give it a list of molecules and it gives you all of the fingerprints for those molecules. By default, that runs single threaded, but there is this num thread argument that you can give to that where it'll generate the fingerprints in parallel. Right. So again, if you want to generate the same fingerprint for a bunch of molecules, this is a quick way to do that. Excuse me? It's less than the cost of sending the individual molecules. So for people who don't know, every time you call one of these functions, you're going from Python into C++, and there's a cost associated with doing that. If you make one call, so this get fingerprints call, the cost is less because it only has to cross the barrier once. So it's more efficient to go this way. No, if the things fit in memory, it goes. It doesn't copy things. It doesn't copy the molecules. So if they fit in memory initially, they should fit in memory here. 4,500. This is new. So RDML processing, this pull request is not yet approved. So this hopefully is going to be in the next release, but may or may not. This is kind of like Paolo's R group highlighting. It may or may not. I promised Paolo it'll be there, but it'll be there. This is not dependent upon me. This is dependent upon the other RDKit maintainers deciding that this is actually a good idea. So this is my attempt to put pressure on the other RDKit maintainers. So you should all say how cool this is. So RDML processing, this is an idea. We know that people do standard operations where you do things like you read an SD file and you generate all the fingerprints and you don't care about the molecules, you just want the fingerprints, right? This is a common thing that people do. Or similar type things, you want to generate descriptors or you want to do something. So the idea here is to make it easy to have a single call you can make where you say, get fingerprints for molecules in a file. You give it a file name, you give it a fingerprint generator if you want, and then it gives you back the fingerprints. So you don't have to worry about constructing the supplier and reading the molecules and calculating the fingerprints. It just does that for you. It recognizes the file type for you. It deals with compressed files automatically. And then it just gives you back the list of fingerprints. It does that. Again, it can do that in a multi-threaded way. So the examples I'm showing here, I'll just skip down to the bottom actually. So this is an example of reading in the SD file from Chembl so that you can download this compressed SD file that has all the Chembl molecules. There's in this particular case, I think it's 2.3 million molecules. So I just call RDMol processing, get fingerprints from moles in file. I give it the file name, and it takes 74 seconds to generate 2.3 million molecules. In the meantime, the fan on my laptop turns on, right? Because this does use multiple threads. So it'll take advantage of everything that's there. So this is a convenience function. Yeah. No, so it does basically what it does, it reads a molecule, generates a fingerprint for it, saves the fingerprint, throws the molecule away. So you only have to be able to fit the fingerprints in memory. You don't have to fit the molecules in memory. If you give this, if you have, the enamine real SD file and you give this and you can't fit 9 billion fingerprints in memory, this is not going to go well for you, right? But that's on you. You have to be able to store the results as it is. You have to be able to store the results that it's generating. We could imagine if it was useful at some point to have a function that reads the molecules, generates the fingerprints, and writes them to a file. We could do something like that, but that's not there yet in this initial version. Emmanuel, you had your. No. So the question was, can you give it an offset to start and terminate at? This is intended to be a simple interface. You can really easily do that by using the supplier yourself. So like if you want to do advanced stuff where you do things like that or skip molecules or do whatever, you can always use the code that's there. This is really intended to be simple. And so it's not going to pick up 5,000 possible options, every possible option. It's going to stay for relatively simple things. And there's a question. You can give it a generator. Oh, sorry, you mean Python generators. So for people online, I'm stalling. For people online, the question was if this would be more robust if it supported Python generators. It's still, because of the way the multi-threaded processing works in the back, it's still going to have to build up the stack of molecules. We could, but so it's open source. Feel free to submit a pull request. That's my trump card. I'm sorry. All right. If there's time for, we're basically. I'm getting. This is Andrea. She's the moderator for today. I'm being moderated. Okay, so I'm going to stop. We'll pick this up in the next session. Thanks, everyone.